Hello students. Welcome back to class. Today, we are going to explore the topic of magnetic fields part 2. But before we get started, let's quickly recap what we covered in our last lesson. In our last class, we learned about the concept of magnetic fields, which are areas around a magnet where its magnetic force can be felt. You can't see this field with your eyes, but it's there, much like the wind. This invisible force can attract certain materials such as iron, nickel, cobalt, steel, and so on. We also discussed the applications of electromagnetic fields, which can be seen in devices like speaker, electric fan, washing machine, and electric mixer. Today's objectives is to explore the concept of Earth's magnetic field and the magnetic force on a moving charge. The Earth behaves like a giant bar magnet. This means there is an invisible magnetic field surrounding the Earth that affects magnetic materials and compasses. What does this imply? If you bring a compass or a magnet anywhere on Earth, it feels this field. That is why a compass needle turns to point in a specific direction. It is reacting to the Earth's magnetic field. Before GPS and satellites, sailors and explorers used the magnetic field to find directions. Sailors use it to set their course across oceans. Pilots also use compasses as a backup navigation tool in the airplanes. What causes Earth's magnetism? Earth's magnetism is created deep inside our planet. The Earth has a very hot, liquid core made of molten iron and nickel. Because this molten metal is constantly moving in swirling convection currents, it produces streams of tiny charged particles, like little electric currents. These moving charges generate Earth's magnetic field, which acts like a giant invisible shield around our planet. This magnetic field has a very important job. It protects us by deflecting dangerous charged particles coming from the sun. These particles are called solar wind. Without this magnetic protection, the solar wind could slowly strip away our atmosphere and make it impossible for life to survive here. For example, Mars doesn't have a strong magnetic field, so it lost most of its atmosphere over time. That's one reason Mars cannot support life as Earth does. So, thanks to Earth's moving liquid core and its magnetism, our atmosphere stays safe, and life can thrive. You're making progress, keep it up. Let's look at some important terms that will help you understand how we find directions using Earth's magnetism. Magnetic meridian. This is an imaginary vertical plane that passes through the magnetic poles and your location. It shows you the direction of Earth's magnetic field. Geographic meridian. This is also an imaginary vertical plane, but it passes through the geographic poles, the true north and south poles on Earth. This line shows the true north-south direction. Declination. Declination is the angle between the magnetic meridian and the geographic meridian at your location. This angle tells you how much your compass needle points away from true north. Why is declination important? If you only follow your compass without correcting for declination, you could end up going in the wrong direction. That's why maps often show the declination for different areas. Navigators and explorers use this information to adjust their compass readings and stay on course. When a charged particle moves in a magnetic field, it experiences a magnetic force. This can be represented in a formula. F equals Q times V times B times sine theta, where F is the magnetic force in newtons. Q is the charge in coulombs. V is the velocity of the particle in meters per second. B is the magnetic field strength in Tesla. Theta is the angle between the direction of motion and the direction of the magnetic field. Let's solve a problem. An electron, which has a charge of 1.6 times 10 to the power of minus 19 coulombs, is moving with a velocity of 2 times 10 to the power of 6 meters per second. It is moving perpendicular to a magnetic field that has a strength of 0.2 Tesla. Calculate the magnetic force acting on the electron. Solution. The formula for the magnetic force is force equals charge multiplied by velocity, multiplied by magnetic field, multiplied by sine theta. Given values. Charge Q equals 1.6 times 10 to the power of minus 19 coulombs. Velocity v equals 2 times 10 to the power of 6 meters per second. Magnetic field B equals 0.2 Tesla. Angle theta equals 90 degrees. Since the motion is perpendicular to the field, the angle theta is 90 degrees. The sine of 90 degrees is 1. Substituting the values. Force equals open bracket 1.6 times 10 to the power of minus 19 close bracket, multiplied by open bracket 2 times 10 to the power of 6 close bracket, multiplied by 0.2, multiplied by 1. This simplifies to 0.64 times 10 to the power of minus 13 newtons. Expressed in standard form. 6.4 times 10 to the power of minus 14 newtons. Answer: the magnetic force acting on the electron is 6.4 times 10 to the power of minus 14 newtons. Congratulations on completing this lesson. You should be proud of yourself. Challenge yourself with these questions. They are a great way to boost your understanding. Today, we delved into the concept of Earth's magnetic field and magnetic force on a moving charge. I hope you found the class both interesting and informative. In our next lesson, we'll continue with electromagnetic fields. Thank you.